Let's start talking about the electric field in specific. Now, whenever we talk about fields, we're going to be talking in general about two charges, so it's important to understand which is which. Now, the terminology I'm used to using is having a source charge and a test charge, but it appears that the book is using the term probe. So I'm going to try to use the term probe, but sometimes I'm going to default to using my old terminology of test charge. So test charge or probe charge is the same thing. So the source is creating a field. And in this case, we're not actually showing the source. There's some sort of source, I don't know, over here maybe. So we have some source charge, but then we have a probe charge. And the probe charge is different. The probe charge does not experience, sorry, the probe charge experiences the field, the source charge creates the field. So they're two different charges. And when we put this into the equation, we have to be really careful about which one we're referring to. So with the notation, this might be capital Q versus lowercase q, which is my favorite. It might be Q1 versus Q2. It might be Q versus Q prime, which is the one the book uses when we do the calculation in a little bit. So what we then say is that this source charge has created a field everywhere around it. And the probe charge is at a specific position in space. Now, what's a little unclear from this picture is that this position, where the charge is literally also that position. It's two separate pictures. Ideally, that's the same position in space. So this has created an electric field. When you place this charge there, it experiences a force. So this charge has a force, the source charge has created the field. There is a relationship between the electric field and the force, which is what we're going to talk about in 2 videos from now, or even right now a little bit. So the force from the field is literally going to depend on our probe charge. So this is again where we have to be really careful with our notation. The Q on the bottom here is the probe charge. It's not the source charge. And the force it experiences goes on top. So we know that the force depends on two things. It depends on the charge itself, and it depends on the electric field. So another way of writing this is that the force equals the charge times the electric field, which is frequently how you're going to see this written. But right now we're trying to define what the electric field is. Now note that the electric field is a vector. So the electric field and the force are both vectors. So they point in the same direction, where one thing to note is that the Q itself is positive or negative. So if this is negative, it could flip the direction, right? So if it's negative, then what you have is the inverse direction, or flipping the direction. Okay, and we'll talk more about that in a little bit when we have some better ways to visualize this. So if Q is negative, you do need to keep track of that. That flips the direction of your force, the relationship between your electric field and your force. So you don't always have to write the subscript of on Q, but here it's helpful to remember that Q is your probe, so that's where your force is actually occurring. So nowhere here have we talked about what is actually creating the electric field. This charge doesn't really care. It only experiences the field at a very specific point in space. So whatever your position is, right? This is the position of your probe that is determined by the field at that point. So we're not always going to work in 3 dimensions in this class, but we frequently will. So keep in mind that this isn't just the field anywhere. This is literally the field at the location of your charge. Sorry, of your probe charge. So this is in a way itself a model that the field isn't something that you can touch. It is a mathematical or even visual model that we're using right now, but it's one that works very, very well, and fields are a model that come up many places in science. So we say that the electric force on a charge is exerted by the field on the charge, right? And again, this is saying that some other charge has created it, but in this case, the on a charge, that's on our probe charge. Okay, so that's on the probe charge. And it is created by other charges. Whatever your charge is that creates the field is never also your probe charge. Now, then the field itself is a vector, so it has a direction. It exists at every single point in space, and a charge does not feel its own field. So we're going to talk a little more next about representations. Note that here we've only drawn 8 points. The field exists every other spot too. We just draw some of those points for clarity. Now, if we have an actual relationship that we want to calculate, we can say that the field is going to have the value E, again, vector value. And then when we have charge Q, we just multiply it by our electric field to get the force. And now note that we think about the sign of the charge, positive or negative, and that's going to talk about the direction. So negative is the opposite direction, which means right becomes left, up becomes down, so on. So this is our electric field model, and we're going to be using it for a couple of chapters, and then we're going to have a magnetic field model that's going to look very similar since most of this is general to fields in general.